Okay. Well, hopefully we'll do a little better in our attendance, but it is Halloween. Happy Halloween. Boo and all that. Okay. So, let's see. All right, first, as a reminder, this Thursday, November 2nd, I'll be on the coast, so for you guys, no different. I just won't be standing right here, but we're still going to have class as always. So I'll be from that room there. So for those of you who are down there, office hours. They're great at getting me reserving me a space on short notice. So I'll spending pretty much all afternoon. So after lunch, so in a few hours before class, in Hardy Hall, room 346. They told me that's a conference room. That's near the offices that the other math faculty occupy. So presumably you know that area anyway. Okay. And I'll see about getting down there on more than one occasion during whatever time we have left in the semester. Okay. And then okay, also, for those of you who are going to do this, I'm going to post it a little earlier, and if I'll just give more flexibility, and I'm not changing the length of it or anything. So we'll be posted also. I'm just going to email it to the whole class on Sunday, November 5th. And it'll be due Thursday, November 9th. So if the just in case the extra early sneak peek might do you good. 6 problems, do any 5. Okay. So for homework 2, I hope to make some progress on grading that very soon, like this week. We'll see how long it takes, because I guess that's where I get punished for assigning you so many problems that now I have to grade them. But I'm gonna hold off on sending things back until I've graded everyone submitted, in case I decide to curve it at the end. Always an option, but never promised. So keep that in mind. Okay, now. So where we're at, okay, not sure why this says October 30th, but that'll be fixed later. Now we're still in the midst of interpolation, but we're coming to the end of that topic. Our second pass through it, and then next week we'll get back into we'll take a second look at numerical differentiation, and then the final topic of the semester. Numerical integration. So still dealing with the whole task of, here's a function f of x, how do we approximate it by a polynomial? By making it match the function at certain points, just because we like polynomials. They're the easiest to work with. So where we just were, as a recap, that was 5 days ago, plenty of time to forget. So now we know can't think today. This bodes well. How to obtain the interpolating polynomial Pn of x using Lagrange or Newton. Also, good x values to interpolate at, given the option, which is not always there. Like the Chebyshev points. and how accurate, or I should say how inaccurate, the approximation can be. It has to be an error formula. That's in that's theorem 6.4.1. That's one of the explorations in that section is to basically, well, I sketch out part of a proof for you, and your job is to finish it. Okay, so what we're dealing with today is how to include any information about derivatives into interpolating a polynomial. So not just require that our polynomial equal our function at specified points, but also a derivative matching or higher order derivatives. That's an option too. So now the thing is that results in a higher degree polynomial, but definitely a more accurate approximation. So if you have that information, at least you have a way of using it. And this is called osculatory interpolation. And then a type of oscillatory interpolation that we're most interested in is Hermite, where you're required to match the function value at all the points that are given, all the x values, and also match the first derivative at those points. So that's our main emphasis in this section. So once we have all that, that's it for at least for polynomial interpolation. Okay. All right. All right. So then we use this to build methods for approximating derivatives integrals, and that's chapter 8. So we'll spend the rest of the semester on that. And part of the overall theme of whoops, dang thing. Okay. How to solve any problem numerically. You ask these two questions. One, for which types of problems is it easily solved? So for example, with derivatives and integrals, the answer is, well, polynomials. Those are the easiest functions to integrate or differentiate. And then the second question is, how do we extend simple cases to a general case? So if we have some function that's not a polynomial, how do we approximate its integral or its derivative? And so we find a way to form a polynomial approximation. So those are the answers in this particular case. And as we get into, for instance, next semester, for those of you who go on into that, we use the same philosophy for solving other kinds of problems like linear systems, differential equations, etc. Okay. So, and our destination that remains the same. Just designing numerical methods for solving these kind of problems. And really, polynomial interpolation is a key ingredient in all of these things. That at least some of us will see. Okay. So just to keep in mind where we're at this point. Okay. Now, need you guys to tell me, how is the homework coming along on polynomial interpolation? As a reminder, tune into your questions page. A few items have been added just today. So any further email questions, I can, if they're general enough, I can add more. But does anyone have any questions here? Or from down there? Wow, quite the quiet bunch as always. So as long as that doesn't mean that you're waiting until November 12th to get started on these things. And that's right, I wouldn't put it past some of you. Okay. So, well, we still have another hour here, so if any come to mind, by all means, shout them out. Okay. Now, let's see. Okay, which section? Okay. Oh, okay, this one? Yeah, and there's some of the submissions I got that this was missed. So, no, I do not want that to be bold also. Dang it. Okay. So there's a theorem in this section. All right, so that's why I put this question in there, to call your attention to that. So there's a theorem that addresses this exact question. So be sure to check those out. Just the statement of it is enough. Oh. Keep in mind, this is something that's one of those things that comes up occasionally, and therefore there's plenty of opportunities to forget it. For higher order derivatives, actually, I'm going to make all this go into a new page. Okay. So. No, I want an actual math symbol. God, I hate this thing sometimes. Okay. But that's notation for higher derivatives, which equals jth derivative. Okay. Yeah, I saw in the submissions that I've seen. I've seen a number of instances of, like, I guess you think of it as right answer to wrong question. So I'll be pointing those out as needed. And keep in mind, is I often get submissions where I end up sitting back a score of 6 out of 8 or 7 out of 8. That you have the opportunity to try to fix that. Before the due date for each one. Yeah. Any other? All right. So there are. So what's going on with section 6.5 on oscillatory interpolation? So so to match the function values and derivatives at a certain point xi. So we list xi multiple times in the divided difference table. So for example, okay, so I'll just make something up here. Let's suppose we have x0 is equal to 1, x1 is equal to 2. So we have two distinct interpolation points, and then I'm going to require that f of x0 is equal to minus 1, f of x1 is equal to, let's say, 3. And so at this point, this is the same kind of interpolation problem that we have been doing. Two x values, two y values, you'd find the equation of a line that fits them. But now I'm going to throw in more conditions. So I'm also going to require that f prime at x0 is equal to 0, and f double prime at x0 is equal to 4. Now, if you look at values of f or its derivatives that are specified, we have 1, 2, 3, 4 conditions. So 2f values, the first derivative and the second derivative. So because there are 4 conditions, our polynomial is cubic. So we're going to look for, I'll call it, as usual, P3 of x. So we need to find the polynomial degree 3 that's going to be unique that matches all 4 of these conditions. Okay. So now the easiest way, it's really a pain to do anything like this using Lagrange-like polynomials. In fact, Lagrange polynomials themselves won't even work for this because you can't take a derivative information into account. You could adapt them, and it actually has been shown in the book for the Hermite case. I'm skipping that because it's just so much easier to construct this polynomial using a divided difference table. So I'll show you how you do that in this case. Okay, now I'm going to try actually creating a table here, and I'm going to need, let's see, how many columns? So x, y, and then divided differences of order 1, 2, and 3. So 5 columns. Okay, so I'm not sure how this is going to go as I type it, but we'll find out. So, whoops. Okay. I was trying to get the setup right here so everything will line up nicely. Let's see, how many rows do I need? I need 1, 2, 3, 4, 7, 8 rows. Okay, and I want to have some headings here. Okay, so my headings, I'll have my x values, and then my zero order divided differences, which are just the y values. And then we'll have first order divided differences that go in the next column. And then we have second order in the next column, and one more column that's going to have our one and only third order divided differences. Okay, at least all of that fits. Actually, I'd like to center this too. Okay. All right. So what I'll do here is I'll start filling in all the information that I'm given. So first, starting with the x values. So I have x naught, which is 1. And then because I have a function value, first derivative value, second derivative value all specified, I'm going to list it 3 times. And then x1 only has a function value specified for it, so I'm only going to list it once. Okay. And now I list all the y values right next to them. So that'd be so -1 will be listed 3 times. Okay. And then f of x1 is equal to 3, so I'm only going to list that once. Okay. Now, at this point is where I start filling in divided differences. Now, the way this is normally done, when all the points are distinct, is I have this minus this value divided by this minus this, but everything's identical. It would give me 0 over 0. So what I do is fill in, instead of 0 over 0, f prime, which in this case is given to be 0. And then down here, these 2 divided differences, same situation. So I have to do it again, 2 rows down. Okay. But then between these two, these values are different, so I can go ahead and compute that divided difference normally. 3 minus a minus 1, so 4, divided by 2 minus 1, so the value I fill in there is 4. Okay. Any questions so far about how I'm filling in these divided differences? So when the points are identical, that means you fill in a derivative value. If not, you just go ahead and do the actual division of differences. And in fact, that first scenario is going to come up again. If I go to the next column, normally I take this minus this divided by this minus this. And again, it's 0 over 0. So what I fill in over here, this is where you have to be careful, and I had to actually fix this in the book. It's not the second derivative. It's 1/2. Well, not in this column. I need to go to the next column. Times the derivative at x naught, which is given to be 4. So in general, if you had to fill in a Jth derivative, it's a Jth derivative over J factorial. Just like Taylor expansion. It's the exact same principle. And that actually goes to that one theorem that one exploration was about. And, okay. Oh, I'm getting all the quiz submissions now. Something to look at later. Yay. Okay. Now this divided difference we can compute normally. 4 minus 0 divided by 2 minus 1. So that's going to give me 4. Okay, so that'll be in this column. Oh, this is bad. This is really bad. Can you see what's coming when I do the last divided difference? I'm going to get 0. So in other words, I'm not actually going to get a cubic polynomial out of this. That's interesting. But that's just because of how I happen to pick the numbers. Well, that's okay. It's not going to ruin the example or anything. I'll just go with it. So this minus this divided by 2 minus 1. So my final divided difference is going to be 0. So then what happens? Oh, can anyone point out my mistake? Well, let's get rid of that because that's contaminated by mistake. Where's my mistake? What? No, this is supposed to be a second derivative, except, but the mistake is still in this entry. What? Yeah, I forgot to divide by 2. So here I'm telling you, oh yeah, you can divide by j factorial. I didn't actually do it. So, yeah, that's a 2. All right, and that's good because now this last divided difference will be non-zero. So 4 minus 2 divided by 2 minus 1, and that gives me 2. Okay. So now what I can do is, so any questions about how a divided difference table was filled in? Okay. So what we have here is, so now the polynomial comes from reading coefficients off the top. So we start with minus 1, so starting from here. And then we have the next one is 0. I'll fill in as like 0 times, just so you see the form of polynomial, x minus x naught plus 2, plus 2, I do not want this to be a subscript. What are you doing? Okay. Times x minus x naught squared. And then you have plus 2 times, so the centers come from these points going down the list. So x minus x naught because of this, then squared, and then we have x minus x naught cubed. Now x naught is equal to 1. Okay, so now if I make this equation array, it'll be easier to work with. Okay. All right, so that would be minus 1 plus 2x minus 1 squared plus 2 times x minus 1 cubed. And then it says could be multiplied out if you want to get into power form, but this is our polynomial that satisfies all of these conditions. That at x is equal to 1, we have these 3 conditions satisfied. And then at the x is equal to 1, that it's equal to 3. Sorry, x equal 2 rather. It's equal to 3. Okay. So just to verify that, okay. So P3 prime. So that would be 4 times x minus 1 plus 6 times x minus 1 squared. And then double prime. So that would be 4 plus 12 times x minus 1. So for instance, if you plug in x minus 1, x equal to 1, then at x naught is equal to 1, then you get 0 here, and then you get 4 here. So the derivative conditions are all satisfied. Okay, so when you are, once you finish the divided difference table, as you're forming the polynomial down here, read your coefficients off the top row, and then the linear factors that you include come from going through the points in order. So first term has nothing. Second one has the factor corresponding to this point. So x equals x minus 1. And then next term, x minus 1 again. And then third term, x minus 1 again. So x minus 1 cubed. Okay. So this is how we handle osculatory interpolation in general. We're given some, so this information has to be given up here to help you form your divided difference table. Now, for the Hermite case, it's exactly this again. It's just of a particular form, where every single point is listed twice. So in this column, you'll still have your y values. In this column, every other value will be a derivative value. And then the rest of the divided differences you'll just compute normally. So you won't have any higher order divided derivatives in the Hermite case. All right. So now for the case of Hermite interpolation, there is an error formula that's very similar to the okay, actually I don't want this. Okay. To the error formula from last time. Okay. Here it is. All right. So, actually, what I'm going to do is I'm going to go back to the previous error formula just to refresh your memory on that. So here's the error formula for Lagrant or Newton interpolation. So f minus Pn is n plus first derivative at an unknown point over n plus 1 factorial times the product of all the linear factors, x minus xi. Very similar to the Taylor remainder. In fact, this part is identical. It's just that now you have n plus 1 different factors instead of n plus 1 identical factors all multiplied together. Okay. Now, whereas in the osculatory or Hermite case, here's your error formula. The easiest way to remember this is everything doubles. Because you have 2n plus 2 conditions now, you have n plus 1 function values to match, you have n plus 1 derivative values to match. That's a total of 2n plus 2 conditions, which requires a polynomial degree 2n plus 1. So I use the letter h, capital H, to refer to a Hermite polynomial as opposed to the other kinds. And the subscript is once again the degree, so 2n plus 1. So everything doubles. So you have 2n plus 2 order derivative, 2n plus 2 factorial down below. And then same linear factors multiplied together, it's just that now they're all squared. Because that goes in keeping with how with a divide difference table for a Hermite polynomial, you're listing every point twice, so that manifests itself right here. And yes, I say here probably what every mathematics textbook reader hates to see. And in fact, I remember someone on Facebook excoriating textbook authors about this. The proof will be left as an exercise. But don't worry, I did not assign it. So and now I'm going to talk about the explorations that I did assign. Okay. So I assigned from this section, and they're all going to be described in the document here, 1, 2, 5, and 6. Okay. So for the first one, okay, use a divide difference table to compute interpolating polynomial for cosine, where you're given 3 conditions to satisfy. So function values have to match at x equals 0 and x equals pi, and you also have a derivative value. So it's 3 conditions, so that's a quadratic. And then you have one more condition that's added after that, a derivative at x equals pi. So 4 conditions, so that's a cubic. So this is actually a whole lot easier for you to do now that you've seen this example that I've just done. So that's the first and most important bit of advice I can give you for this exploration. The only difference is, instead of having a first derivative and second derivative value at one of the points, it's the derivative at both points, a first derivative only at both points. But same kind of divide difference table, and then you form a polynomial in the same way after that. There's another example in the section for Hermite case, and that's a good one to look at also. That would be example 652. So both of those are relevant. Okay. Now, number 2. Okay, so this is a more general question about oscillatory interpolation. In fact, for this also, it would be a good idea to look at the example that I just did. So now, this is like an extreme case of oscillatory interpolation, where because in, so to speak, regular interpolation that we have been doing, all the x values are distinct. Now, oscillatory interpolation allows them to not be distinct, because now you're filling in derivative values. So let's take that to the extreme. Suppose you only have one distinct interpolation point, x naught, and you're specifying derivatives up to a certain order. So f of x naught, f prime, f double prime, all the way up to the nth derivative. So now you're going to get a degree n polynomial still, but what is the approximation that you'll get? And so it's going to. So what I would suggest for this is for this one, try an example yourself for a specific value of n. Let's say, actually, yes, say n equals 3 is a good value. That'll be enough to see the pattern. But leave it generic. So in other words, like Pn x naught is equal to, don't fill in numbers, but just leave it like f value, like something like that. So actually literally put this in your divided difference table, and then Pn prime of x naught is equal to f prime x naught, etc. So so the idea is work that out, and what you get for P of x should look familiar, and so then you should have your answer to that one. What you saw here might give you an idea also, but it's a little harder to see just because I didn't make it generic. I filled in specific numbers, but if you took out the specific numbers, like if I fill in here f of x naught, and I don't want that to be a subscript. What are you doing? Okay, is equal to -1. So if you took out the equals whatever and just worked out the polynomial only for these points, like just for these 3 points, xi is equal to 1, and just left it at that, I think that would also give you an idea what the answer is in general. Okay. All right. Is there any questions so far? What? Oh, no, just give the answer. Well, you should show me something as to how where you got it from instead of a guess. So, but yeah, but yeah, I'm not looking for some big elaborate thing where you like prove it or anything. Nothing like that. So if you like, for example, if you do an example like this, and then, based on this, it's that's fine. Okay. Suppose if I really want to be dastardly, I could say, okay, now prove it by induction or something. But I guess I'm having to do that in other problems, so that's enough. Okay. And so now a couple. So the other explorations in section 5 and 6 are coding problems, but these are going to be very similar to what you also are doing in section 6.3 for Newton interpolation. And actually, I changed the wording of this problem to make that resemblance clear. So in 655, you're taking a function that you will have already done from 636, div-diff. Now what div-diff does is it takes in x values and y values, and it creates the divided difference table and returns the coefficients from the top row. So now what you're going to do is modify that to create a new function, div-diff, so for the each case, and you take as input x values, y values, and y prime values. So in that case, you'll fill in derivative values where needed. So let's talk a bit about how you're going to modify this div-diffs function to get to get this one. So, okay, so you're going to modify div-diffs to account for derivative values. Now, so let's take a look at the algorithm that you're implementing for this function, for div-diffs, so you get an idea of what to do, what has to be changed. Okay. All right. I should refer to the algorithm. Okay, this is the algorithm you're implementing for the function div-diffs, where you're computing these divided differences. So you have this minus this or this minus this. So we've seen what happens where you have to fill in derivative values. Then you have a problem where when the x values are the same. So here's what you can do is, if you look at the pattern that you see in divided difference tables for the Hermite case, what happens is, in the first column, you're filling in your x values. Your second column, your y values, f of xi. Third column, that is either first order divided differences, which have f xi x I plus 1, or derivative values. Okay. So what is the pattern? How do you know which one? Well, I'll show you an example that tells you. Okay, so if we go back to Hermite interpolation, so I have an example here in the text of, here's this third column that I'm telling you about, where we fill in the first order divided differences or derivative values. So notice the first 2 points are the same, so the first entry in this column is a derivative. Next two, not the same, so that's a regular first order divided difference. And the next one, identical values again, so that is a first derivative value that goes in there. So notice, so note that every other value is a derivative. Starting with the first one. The other thing I want to point out is, if we go back to the algorithm that you're modifying, okay, so here's the algorithm again. Notice that you're filling in the divided differences. Look at the inner loop here. For I equals n, n minus 1, etc., down to j. In other words, you're starting from the bottom and you're working your way up. And the reason why is, and that makes it possible if you want to save storage, and I actually put in an unnumbered exploration here that you don't have to do, but it could be done to, instead of storing these entries in a matrix, which is fine for this problem, you could store them as a vector and you're overriding divided differences that you won't actually need later. But the point I want to make here is you're starting from the bottom. The last divided difference in that column is a derivative value. So for I equals n, it will be. So as long as you recognize for alternating values of I, you're going to do something different, going back and forth. Derivative, first order divided difference. Derivative, divided difference, and so on. Then you'll fill in the table properly. And this is only for the case where j is equal to 1. Only do this for j equals 1 in algorithm 634, which is what you're adapting for this problem. Because everywhere else in the divided difference table, you're just proceeding normally. You have distinct x values. You can leave that alone. So basically what's going to happen is your erm divs diff function will be exactly what you do with this for div diffs, but you'll have a special case, like an if statement. If j equals 1, and I has sort of a correct value, like again, every other value, that's where you're going to fill in derivative values. Otherwise, proceed as before. Okay. So use an if statement to know when to fill in a derivative rather than a regular divided difference. Okay. And I'm hoping that by the time you get to the problem from 6.3 where you're implementing div diffs, that all of this will become more clear, and hopefully, well, I know some people are working around that part of the assignment already, but hopefully the rest of you soon. Okay. And finally, okay, well, number 6, actually there's not much to say about this one because there won't be very much for you to do in it. It's very similar in spirit to exploration 639 because what's happening is you're writing a function that does a fitting of an Hermite polynomial, and just like one in 639 that's called Newton fit, it's passing a buck. That you'll pass your x, y, and y prime values to erm divs diffs, and it already says to use this function, to get the coefficients in the Newton form, and then you pass those coefficients to power form, which you will have done earlier, and then that'll convert to power form, and then those coefficients are the ones you actually return. So, so very little to do. So you pass input to divs diffs. The output is vector of coefficients in the Newton form. Pass those to and centers to power form. Okay, whoops. Okay, and that's power form is something that you implemented from 638 to obtain power form coefficients, which are okay, and again, that's going to be a vector. And those are returned as output. Now, the only wrinkle here is what are the centers? So in Newton interpolation, they're just the interpolation points. Although you only go as far as the second to last one, because you need to have n centers altogether. Your polynomials of degree n. But in the Hermite case, same x values, except you have to list them twice in this order. And you need to have 2n plus 1 centers altogether, so it goes all the way up to x n minus 1, listed twice. So at this point you have 2n centers, and then you have xn listed only once. So that's the distinction for a grand total of 2n plus 1 centers, and then you're done. So you just have to make sure, because diff, your divided difference function, takes exactly the same input as this function. You just go ahead and call it. The output to this is going to be the coefficients, and you have to make the vector of centers to go with it, and those two items you pass as parameters to power form. So you have to make the vector of centers yourself, so this is how you fill that in. Okay. Now, there's one other comment I should make about this function. It actually applies to, actually this has to do with power form. It's going to be used for both this one, for this exploration 656 and also 639. So a function that is convenient to use. Okay. Actually, I'll put this on a new page. Power form 638. So you pass coefficients and centers to a function I recommended that you write a separate function for nested multiplication. That's algorithm 636. Now what happens is, for polynomial degree n, you need to perform nested multiplication n times. This is what's come up in the reading for those of you who submitted that. Now, what happens in between? After each time, you must change the vector of centers. So first time, so before first nested multiplication, all right, I gave that vector of centers earlier, x0, x1, x2, up to xn minus 1. Before the second nested multiplication, what you need to do is you need to include 0 as the first center, and then x0, x1, xn minus 2. And that's so then that falls off the so xn minus 1 falls off the edge. I mean, that keeps going. So you have 0, 0, x0, x1, xn minus 3, and so on. And the end result is 0, 0, all zeros, n of them. Okay. So a particularly convenient way to do this is using colon notation, and also the using the keyword end as an index. So it would go something like this. So if we assume x is your vector of centers, and what's passed in is this. So to update it, what you can do is the following: is x is equal to, so you start a vector. So, and I'm going to assume, just for convenience, and you can do either way, but it's important to be consistent. I'm going to assume this is a row vector. Okay, so to update it, you could so you want 0 to be the first element that needs to precede everything that's fair, And then what happens? You want to take this whole vector that's there except for the last element. So if this vector has x as n elements, you want to take the first n minus 1 of them. So what you can do is do x, and then you're accessing elements. So 1 colon, and then n minus 1. So end, in this context, when you're using it as an index, refers to the highest possible index. So it's going to refer to the last element, whatever that might be. It'll figure it out for you. And then, but I want the second to last element, so that's why I'm subtracting 1. So all elements from the first up until the second to last, and then 0 is stuck in front. So you can just keep doing that to update your centers in between calls to nested multiplication. And that'll maintain your centers for you. And what will happen is we get to the end, and they're all zeros. Okay. So any questions about this little snippet here? Okay. All right. Now, since I have some time here, and you guys don't seem to have questions, so I want to point out, so we have these explorations that I've been covering in each of the sections. Don't forget, at the very end of a chapter, so this is labeled as section 6.8, but it's not like a section of text. It's only exercises, and these are the 6 that I assigned, 1 through 4, 8, and 10. So I'm going to take a peek at those and see if there's any preemptive suggestions that I should give. So these are the exercises here. Okay. So for instance, so it's 1 through 4, and then 8 and 10. So the first one, so here you're just going through a process. It's strictly a computational problem. But what's interesting here is you're approximating a simple function x to the 4th, but with a lower degree polynomial. And actually, I did an example like that. I approximated x cubed using a second degree polynomial. And what you saw is that at those points, of course, it matched, and in between, it matched pretty well. Away from those points, not so much. And doing it 2 different ways, using Lagrange polynomials, and then Newton form, that is the divided difference table. So we worked through Lagrange polynomials in class before, and by the end of class, you seem to see the pattern behind it. So that's the pattern you're going to follow for the first case. And then for the second case, well, you've seen your share of divided difference tables lately. Problem 2, similar idea, Hermite interpolating polynomial. Oh, I goofed here. Can anyone tell me, okay, there's h3 of x, that's the 3rd degree, so you have 4 conditions. You need to match the function values at 2 points, and then the derivative values at 2 points. Can anyone tell me what information I should provide in here that is missing? Well, p3 of x is what you would compute, but what information do you need to even start computing it? What? Yeah, the x values. I forgot the dang x values. Okay, I'll go back and I'll fill those in. Actually, what I plan to do, what I really intended was here in this problem, using points 0, 1, 2, and 3. So I would use, so what I'm going to do this problem, I'll put it in here. x0 is equal to 0 and x1 is equal to 3. So the endpoints of this. Basically, you're approximating x to the 4th on the same interval, 0 to 3, using the Lagrange interpolating polynomial and the Hermite interpolating polynomial. Both will match at 0 and 3, but they'll match other things differently. They'll match, so this polynomial will match at x equals 1 and 2. This will match derivatives at 0 and 3, as well as function values. So you'll see some difference in the approximations there, but hopefully these both be reasonably accurate. And that's why I want to have you plot them on the same plot so we can see, you can compare how they do at the same points. Okay, so whoops. Glad I took a look at these. Okay. Problem 3, I showed you the error formula earlier. So you're going to use that to estimate the error. Okay, and actually, okay, what I need to do here is it's theorem 641 for this polynomial, and a similar theorem in 6.5 for this polynomial, or meet. So they use different error formulas. But okay, sorry for mistakes here, but at least you have. I assume no one has gotten to these problems yet anyway, so because they're not due for exactly 2 weeks. So figure I was safe there. Okay. Okay, this is something we kind of talked about in class. How you evaluate a polynomial this way, like a straightforward way, as I never pointed out, as written, as opposed to Horner's method, and comparing the efficiency of them. That came up in a reading as well, so there's not really much to talk about there. But I would suggest, like it was done in class, going through an example, so you can see actually do a couple examples for different degrees. And you can see, okay, how many multiplications are required, and what's the pattern? How does the number of operations increase as you go from one degree to the next? And that gives you an idea of like how many multiplications and additions are required in general. Okay. Okay, so I'm going to make these notes here for the okay. Oh, totally spelling everything wrong here. Okay. So 1, 2, 3, 4, 8, and 10. Okay. So for whoops. Okay. For problem 1, basically follow examples in section 6.2 and 6.3 for how to work those out using like Lagrant polynomials or divided differences. Forgotten information, we'll add x0 is equal to 1, is 0 rather, x1 is equal to 3. Okay, for problem 3, we're estimating the error. Use theorem 641 for polynomial. Now, in exercise 1, you are you're computing a polynomial 2 different ways, but it's the same polynomial because the interpolating polynomial is unique. That's a good way to check your answer, that you should be getting the same thing in both cases. And using theorem 6.5. Okay. 651 for polynomial for exercise 2. Okay. Problem 4, what I suggest for that one is try for, like, for instance, n equals, try for a couple different degrees. How does the number of additions or multiplications increase as the degree increases? Okay. Okay. And then number 8. Okay. Write your own Matlab functions to implement the built-in functions polyval, polydir, polyint. Now, polyval, all that does is it takes in x values. It could be a scalar, it could be a vector, it could be a matrix, and it plugs them into the polynomial, and you're given the coefficients. So for your own polyval, you should give these different names. Like what I often do, if I'm implementing my own version of a built-in function, I put a my in front of it. That's my version of polyval. But you can name it however you want. Okay, so for my polyval, use use dot exponentiation. To raise a given input argument x. Because the idea is you don't know what x is. You can't assume anything about it. All you know is it's either a vector, scalar, or matrix. But as long as you use dot exponentiation, it doesn't matter. You can raise any of those to a power in that way, to whatever power. Now, for all functions, input is a polynomial p, and you can assume as a vector, a row vector of coefficients, highest degree first. And that's because that's how these all Matlab's polynomial functions work. So what will happen is, though all these take as input, and then my polyval also takes in x as the second input argument. For the other functions, my polydir and my polyint, all these do is compute a new vector row vector of coefficients from the given row vector of coefficients. All you have to do is use the power rule, either for differentiation or integration, whichever one is appropriate, to compute the new coefficients. So, because you know what polynomial you're supposed to get if you take the derivative or take the indefinite integral. So you can just work out those coefficients and put those in a vector, and that will be your output. Okay. And finally, number 10, I only assigned parts A and B because this part C deals with a section I didn't cover. So what you're doing here is so run this example. We've actually seen this in class, and there's some code at the beginning. Whoops. Oh, I see what happened. That's kind of strange. At the beginning of section 6.4, that helps. Because what it does is it generates a plot of a function, and also like plotting the interpolating polynomial. And okay, so you go ahead and use that. So you're plotting two polynomials. First is Lagrange interpolating polynomial with equally spaced points, 0 to 10. And then the second one is using the Chebyshev points. So you got to figure out the 11 Chebyshev points mapped to the interval -5 to 5. And then you can interpolate at those. So the idea is you're going to compare these two polynomial approximations of the same function. They're going to match at certain points, the same number of points, and you should see one approximation is much better than the other. And what I will do to make this a little easier on you, you're allowed to use polyfit, but bonus if you use your own function Newton fit from exploration 639, which is supposed to do a similar job. In fact, it does exactly the same thing. You give it x's, you give it y's, and you get the coefficients of a polynomial. The output exactly the same, or it's supposed to be if you implement it correctly. The only difference is polyfit has a third argument that's the degree, n, whereas that's not required for Newton fit because the degree is already assumed to be n, where n is the length of your vector of x values minus 1. Okay, so and that works out beautifully because I've come to the end of time. The end of class time, not the end of time. So, all right. So hopefully you guys will be making progress through the homework, and so you won't be so dang quiet next time. Or if you have questions in between, be sure to send them my way. So I'll see you from a distance. Well, you guys from a distance, and you guys up close on Thursday.